results which I'm happy to share in this conference. So with Silu kernels, we have basically the similar problem as before in when we execute large language models. Lots of these things are on the CPU. Just to repeat that, the Silu kernel is used very often actually I see it in combination with AvgPool2D and Silu, so that's even a very common kernel of so or operation, let's say. So that's why we picked that operation as well for our fusion operation. And so the problem remains. We basically go back and forth between GPU and CPU, and have this overhead, as we talked before. So this overhead now, again with AvgPool2D and fused with Silu now, we see a little bit better results here as before with the Relu kernel. So it makes much more sense to do AvgPool2D with Silu, because the improvement is actually a little bit better. So here's I did the pictures at a different time, so they look slightly different, but it's essentially the same as before. So when we come from a CPU, we transfer the data through DMA, engage the GPU and the single a kernel which contains AvgPool2D and the Silu. So and that combination provides us the actual acceleration of this combined kernel. In addition to that, just by sending it to the GPU, we have a huge acceleration achieved already. So here again, the different kernels which we are implementing. We already showed that we implement AvgPool2D. We also have Silu in C++ for CPU and Silu on the CUDA in CUDA, but then also we have AvgPool2D with Silu in CUDA. The implementation is a template, so it basically supports different integer as well as float types. So we can basically just, because it's templated, we can just basically put in the type we want, and there's actually integer types, 32-bit, 64-bit integer types, the double type, but then also in CUDA we also have between the different integer types 32, 16-bit, 8-bit. So all these are implemented or supported due to the templatized format of the kernels. Also, what I want to mention is lots of LLM models actually use integer types, and they basically replace the float type. Maybe the original model is trained in a float type, but then it's replaced for power savings and for optimization purposes is using integer types. So to support integer types is very important in this environment. Nevertheless, the results are using the 32-bit float type. That's a normal IEEE 764 based IEEE 32-bit float type, which is kind of the standard type. So in Silu, we have a more complex. Silu is a little bit more complex. It's these activation functions look very often very similar. We saw before that we had the maximum function, but with Silu, we have a little bit more complex function. We have the exponent of minus x here to calculate, and that basically we can show the curve here on the right side. So the complexity to calculate this versus a maximum function is a little bit higher, so we can see that actually in the results as well. So we looked at the average, so this is exact same average pool 2D kernel as before, with KH and KW being the size of the kernel itself. So here's this, now we see here the difference. So the left side is the same average pool 2D. And what happens now is we apply the Silu function, which basically reduces it's very close to the original number 5.5, but it slightly reduces the number 5.47. If you extend to the limit of Silu, eventually merges with the exact number. It's basically an identity, but it basically reduces that number. Nevertheless, if you do a negative number, it basically will end up also into first of all a little bit negative. Unfortunately, I didn't put a example here. A little bit negative, and then the limit is if it's going further negative, it goes to 0 again. So very similar functionality, but it has the negative component, which the max activation function does not provide. So again, very similar what we saw before. The average pool 2D, we saw that before, has on the CPU, obviously very linear, very nice linear relation between of the size and timing. But then on the GPU, we see again very compact here between 0. I would say 7.5 to 0.115 seconds. So it's very much related to noise. So and then including Silu, we see a little bit slower because we incorporate the Silu. Here we also get up to 1.015 here. So so the impact of Silu on the operation has a little bit higher impact than what we saw before with the Relo operation in the last presentation. So, and these are now showing the fused kernels. Again, now we can compress it again back down below 0.15. I think the impact here is a little bit higher than with the Relo kernel versus the Silu kernel. So the impact here seems to be more because the kernel itself is more complex. The Silu kernel is more complex to calculate. So it has a higher impact on the overall result. But again, if we look at the overall result, comparing larger matrices here, or larger data sets, so 3072 by 3072. I'm sorry, I forgot to mention that this is based on dx and dy being dy being 3072. So this basically shows a huge impact on these larger matrices. On the lower end, if you go to 256 on this in one dimension, at one point we reach the point where running it on the CPU is faster because of the overhead we already mentioned. The overhead, so this we can hardly see a difference here it goes up slightly, but it's very hard to see in this scale. But we can clearly see here that if you have a very low number of or the matrix is very small, then we basically it is cheaper basically to run it on the CPU and not to give it to transfer it to the CUDA or to the GPU. And this is purely because of the overhead to engage the GPU. And we can say that we are basically that if the portion if in the future we may use more fuse actually more kernels so they that they run directly on the GPU, which basically would mitigate this area here. So you basically get a more this moves further to the left, let's say. So yeah, so this was just an extension of the other presentation. So we are basically building this. So we are basically seeing the general idea. Nevertheless, it's really with a kernel. The fused kernels have an impact on what the impact is and how much improvement we get through fusion itself. In this case, we can see about a 30% improvement. So we see much more impact because the both kernels are or the I'm sorry, the Silu kernel is in fact somewhat complex because it has the exponent function, it has division, so it has some complexity to it, and therefore the running it in parallel um, on a GPU makes a difference, and even more so if we perform the fusion itself. Nevertheless, again, with these type of operations where you have some pooling function and a activation function, the communication overhead, you basically send the data to the GPU. The communication overhead is really dominating, and shows the huge variance. Uh, and kind of I would say noise. So there's more measurements maybe and maybe better ways to measure it to make a better conclusion. So this is showing a general trend on how to do it, but in the future we may need to do more measurements and we believe that the impact is much larger in real LLM models, and also what we think, because some of the matrices are really huge. So with these very large matrices and models, I think the impact can be very significant. So I think the path, this is the right path we are on, but some of the things we need to figure out in a sense how we measure it and which operations to fuse. Some kind of don't necessarily make sense to fuse. They may not be relevant, but also the overhead may not be, or the results may not provide enough. The difference may not be big enough to warrant the effort to fuse those kernels. So yeah, but we are basically moving on with our library in that sense, and so the next step really I would say is take these fused operations and integrate them into a real-world LLM model so that we have comparisons with models which are actually used in the field. So that's yeah. Thank you.